Team has grown and grown and grown each year, and I'm really proud to bring up our team that's here. It doesn't include everyone at American Governor. We have people still out in Pennsylvania, still doing actual work, and but I want to bring everyone down, so come on down, team.
It's all of us.
I used to spend a lot of time on intros on each person, first, last name, experience. I can't even remember everyone's name at this point. But this is our team. I am not one of the trainers, and if I'm ever in your plant, do not let me touch anything. Okay? So I'm going to go just around the list, around the line, and we'll start with Jim. And there's Jim's one of our digital guys, and we got Craig who does our purchasing. We got Mike Mono hiding behind Craig. There he is. We got Veronica, who's brand new out of our Pennsylvania office. We got Mikey G, one of our new young engineers. Chris Kreider, one of our road warriors. We got Mike Lassa. He's our lead production repair out here in Amherst. Gary Rosenberger, one of our bright young engineers. We got Debbie. Debbie's on the sales side. Debbie, don't let Debbie touch anything, including your computer. And Roger, he's on the sales side again. What does that mean? No touch. Kelly's out of our Pennsylvania office. She pretty much runs everything out of there and, well, everything throughout the company. And I listen to everything that Kelly says, and I strongly advise you to do the same. Matt Roberts. Matt's out of Pennsylvania. He runs our engineering and production out there. And we got Paul, another one of our super stud, bright, young engineers. Anyone hiding back there? There's Rick. You met Rick. Hi, Rick. And we got Bill. Bill is one of our future stud engineers. Bill is one of our, we have a number of co-ops and interns, and it's one of our, we pretty much hired everyone who knew anything about governors in the industry and say, we still need more people. So we created our own assembly line of engineers. So we have a very strong co-op program with, we work with several universities, Drexel University, Cornell University, and Penn State, and we have 5 of these guys here. And maybe one day, after we put them through the ringer and see what they're made of, maybe one day they'll be an official American Governor employee. But there's Bill, and there's Evan. He's another one. There's Joe, and Manny, and Evan. I mean,
Good.
Dave. Yeah, Evans, yeah. Well, I'm glad you all 5 lined up in a row. That was perfect. Jess, she's on our marketing end and international sales as well. And so we got Sarah. Look, I can't remember anything, so it's amazing I made it like all the way to Evan. Sarah, she pretty much runs everything out of Amherst, and you should listen to her too. We got Travis, and he is our new IT stud. Thank you, Travis. My computer works now. We got Kirk. Kirk is one of the old-time Woodward guys and knows a lot about a lot of stuff. We got Lori out of the West. We have 3 people out of our Northwest office in Seattle. She's in sales, so you know what that means. Bianca, she is in the engineering group out in Pennsylvania. Then we have Dana, who is also out in Pennsylvania. We have Jerry.
Me, Dan.
I said, you know, we have a lot of experience from Woodward Governor. I think we might have 500 years plus experience.
Oh,
Jerry has 150 of those years by himself. And we got Dan Berrien, engineering manager out of Pennsylvania. And Dan's going to be giving the Droop presentation. And we got Alan Fox. He is in sales, but he was a service guy of some sort, but just in case, don't let him touch anything.
Nothing important.
Yeah. We got Dan Chicky right here out of Wisconsin. And we got Steve, who is our operations manager here in Wisconsin as well. We got Joe. Hi, Joe. Another one with a lot of years of experience. And this is our team. We're missing maybe about 10 more people throughout the company and different places. A couple people are traveling. Got Bill in Ireland and a couple other people out and about. But this is our team. I'm really, really proud of these guys and girls, ladies. And so I want you to give these guys a round of applause. Many of these people are going to be giving you the classes this week, which leads me right to the schedule. I personally scheduled most people here. Is there anyone who has not talked to me either on the phone or here about a schedule? Good, we got like 3 or 4 people. You know, come see me afterwards. I do need to reschedule a few people. Folks from Grand Coulee, I just want to move a couple people around because I want to make sure the hands-on sessions don't have 20 people one day and 10 people the next. So Brady, Chamberlain, DeSauter, Langhurst, Mata, Stolhammer, all from Grand Coulee. I'm going to switch you guys just to your classes. So come see me afterwards. We have 3 days of great classes. Today, everything's pretty much contained here, and you're contained, and everything's sort of in control. It will be a little chaotic and hectic over the next couple of days. People running here, people running there. We're going to really try and keep it together. If you have any questions about where you need to be, where you need to go, I'll tell you where to go. We have mechanical cabinet actuator sessions. We have gauge shaft sessions, analog sessions in green. We have digital sessions in purple. We have Pelton sessions in blue. Some of the classes repeat, some of them don't. I'm pretty sure everyone has a good understanding of what they want to do and what they're going to do. And so I'm not going to go into any real detail, but it's going to, as soon as you break up into the different sessions, it's a lot of fun. And you know, we want you to have a good time. We want you to learn a lot. And you know, welcome to our 10th annual Governor School. So thank you. This is the largest class we've had so far by about 2. I think we have 106.
Can I go into
Oh, we did?
mode?
Wah, wah. Second largest.
And Brad, I'd like to see what's coming up next.
In 10 years, 800 people in this
Yep.
industry.
About 800 have made it through. And with that, I'm going to turn it over to Dan for the Continue Governor 101 and Droop.
That's the old one. There you go. Oh, nice. That's awesome. So the next one just is there. That's great. How's my microphone? Should I just use the handheld? Microphone on? There we go. That I'm not talking into the mic?
Yeah, because you move your head away.
Well, I'll put it on the right side, so it'll be.
Yeah, so
I'm going to be facing this
try
way
to,
most of the
yeah, try to turn it
time.
down.
Okay.
And I want you to stand a little more behind the podium.
Great. All right, how's the volume out there? Can everybody hear me? Yes, yes, in the back? Very good. All right. Can we get the house lights? Thanks. Well, as Scott said, I'm Dan Berrien. I'm out of the Pennsylvania office, and I have the distinct honor of putting you to sleep right after lunch with permanent speed droop. This is not the slot you want to be teaching a topic like this, but we'll do the best we can and try and get through it. Permanent speed droops, it's kind of a rough topic, and even people in the industry who deal with it all the time don't necessarily have a good grasp on it. So we're going to try and present it in multiple numbers of ways so that if you don't get it as it's shown to you one way, maybe you'll understand it in another way. And after this, Jerry's going to talk about compensation. And because droop is a form of compensation, he will be touching on it a little bit again, just from a slightly different point of view. So if you don't quite understand it after this, first of all, I'd like you to ask questions at the end if you don't quite get it, and we can backtrack and talk about it. We got lots of time. But hopefully one of these examples will become clear for you. So we're going to run through the presentation. First, talk about a little bit of background about different types of grids. Then I'll go into the definition of droop, just the esoteric definition, the basic, something you find in Wikipedia. But then we'll talk about the needs. I'll give you some mechanical examples, run through a case study using some dancing saws and a bunch of wood. Then we got load sharing, how it actually applies to a real-world application that we all live in with power generation. We'll talk about checking the droop, and then show you a real-world example of how it'll apply to your day-to-day life, and show some actual graphs of samples that were taken, so you can see what the governor actually does over the course of a day. First of all, we got an isolated power system. It's defined as one machine supporting a load. There aren't too many of them out there that people deal with. Maybe when you're running your house units, you could call that an isolated system, or some like a heater in a remote plant that just runs. You're not actually generating power, but you're just carrying the single load from a single device. Or it could be multiple devices, but you basically have one generator on the system. Small system is more common, especially in more remote places like the Northwest Territories, where you have a few machines running a local load, and you really want the frequency to come back and be stable and respond well to load changes. Then we have the large system, where we have many machines interconnected. That's what most of us are used to working with. I mean, we all kind of assume on the large systems that the speed of the grid is stable, but it's just not true. It actually slides around. It's relatively stable, but it can easily slide around throughout the day between 59.98 and 60.02, and that's in a good place. That's like in Pennsylvania, we plug into the outlet, we're going to see the frequency drift up and down throughout the day, rather quickly too. You can almost see when somebody makes a correction to the grid because your fluke meter takes a little hop, and it's like, oh, look, we got a new frequency set point here. But then you get somewhere down in Texas, some of the interconnects, we've seen it slide around quite a bit more. So the assumption that the grid is going to hold exactly 60 hertz is not true, and that's very important as far as the discussion of droop. So the basic definition of droop is you're going to see an automatic reduction or increase of the speed setting as the gates open and close. So as your gates move, there's actually a feedback mechanism that comes in and affects your speed adjustment setting. And I'll show exactly how that works and why we need that in the following slides. then the amount of speed droop is defined as the percent of change in unit speed for a full servomotor stroke. So if you're running 5% droop, it would take a 5% speed change, which is huge, absolutely huge, to get your gates to go from like 0 to 100% or 100 back to 0. So it's basically the definition of the curve that it's going to follow. Now, one important thing is that it does not change the sensitivity of the governor. Sensitivity is a whole different issue where it's how much, like the accuracy that you can detect speed. Like if you can go down to the third decimal place in the speed, that's more of your sensitivity. This is more of how much it reacts to a change in speed. So it's not the sensitivity, it's actually how much corrective action the governor is going to take when it sees a change in the speed. So let's try and not get those confused. You're not disabling the speed sensing on the governor as you increase the droop, you're just changing the reaction that it's going to have. So it's basically a tunable parameter. So here's a classic effect of two units on a large grid. And up top, we show how the grid speed changes. We're sitting at 100%, and the unit number 1 is at 2% droop. It's sitting at that gate position. Unit number 2, sitting steady. Now, as the grid speed drifts up, you can see that the units are going to react, and the unit with 2% droop is actually going to move a lot more than the unit with 5% droop. But you see that when the speed stops changing, the gate position evens out and the units stop reacting. All right? So for a given speed and change, you're going to have a proportional response to that speed change, but then it stops. So the 2% droop unit actually moves more than the 5% droop unit. Okay, now that doesn't really help you understand exactly why that happens. We'll cover that later. But if you look at this chart, as the speed goes back down, you're going to return to your normal set point, assuming nothing else has changed. So once you're back to 100%, the gates are going to go back to where they were before you saw the speed disturbance. And conversely, if the speed drops, you're going to see an increase on the units. So as the grid speed moves throughout the day, you're actually going to see your gates open and close in response to that. It's not that the governor's drifting or out of calibration, although that could be the case. But assuming a good functional governor, your unit's actually going to move with small changes in grid speed. Now, the need for droop, basically, there's a number of purposes that it serves. It actually is a form of compensation, so it adds stability to the turbine control system. The changes in the gate position are used as feedback to come in and provide stability. So as the gates move, we adjust our speed reference, and it helps have a calming effect on the governor, and that allows it to stop at the desired gate position. It helps compensate for water starting time and machine starting time, as Jerry will talk about those later in the stability discussion. It also allows us for multiple units to share load together. If we didn't have that automatic feedback mechanism in there, all the units that you have online, you'd change your speed reference, and it would want the turbine speed to increase to that number. So basically, if you were sitting at 100% speed and you give it a speed raise, the gates would start opening, because you're waiting for the speed to actually change. But you're on the large grid, and you only get small changes, not large changes, and you'll never satisfy your governor, so you'd go wide open. Conversely, if you backed off the speed adjust, you would drift all the way closed until the unit was unloaded. All right? So what it is, it's a feedback mechanism to basically say that it's okay to stop at a gate position when you're not at 100% speed. Now, with the speed held constant, you start manipulating the speed reference, and that's how you actually can have a gate position set point value when you're online. So that's how you can change the load of your unit when you're connected to a large grid, because this droop feedback mechanism. Now, I know that's just a lot of words, and it's probably not real clear at this point exactly what's going on, but this should help clear things up. We got here's the typical gate shaft GS actuator arrangement here. And let me point out some of the highlights. Obviously, we got the servo motor And the feedback comes in to your speed droop cam, which means that as the servo motor moves in and out, this cam is actually going to rotate and move this lever up and down, right? The whole platform here slides up and down. Now what that does is your speed reference adjustment is actually sitting on that platform, all right? And then the whole assembly, obviously the ball head, I'm sure you have seen plenty of pictures of those already. Ball head's up top, and then you have your floating lever, or your connecting rod coming down to your floating lever, all right? And here's your pilot valve. So as the servo motor moves up and down, this cam will rotate and cause this to move up and down in proportion to the servo motor stroke, to how much it moved. And then that'll actually would be the same thing as cranking your speed adjust up and down. So here, that's where those initial words in the opening slides came from, that it's an automatic increase or decrease of the speed adjustment as your gates move. So you can see how that's accomplished. As the gates move, this cam rotates, and it's almost as if the operator was sitting there, turning the crank up and down. Now, what's going to happen here is that's going to have an effect on the pilot valve. So say the operator were to take that manual adjustment and give it one crank to the right, all right? That would compress the spring, which would then lift up on the pilot valve, all right? Because nothing's moved yet, but because he increased the spring force, he's going to lift up, and it's going to cause the pilot valve to move in the opening direction, which will cause the servo motor to go open. Now, as the servo motor goes open, this cam's going to rotate, and it's going to drop this section back down, which is going to relieve the tension that you just put in through the speed adjust assembly. So you make a change, the gates move, and the automatic feedback that we call Droop pulls your change back out. Now notice that your speed hasn't changed, all right? So what we did is we just made an online adjustment which changed our gate position without changing speed, all right? And it automatically went to its new position because of this cam assembly. Now as you change the setting of this cam, this is how you change your Droop number. If the cam does nothing, if when the servo motor moves, you get no motion whatsoever out of this cam, that's 0 Droop. You've taken all your feedback away, and you are completely dependent upon speed changes to get rid of your speed adjustment request. All right? Conversely, if you put a tremendous amount of Droop in, say up to 10%, it's going to take much less gate movement in order to get rid of the speed adjustment error that you introduced. Or, if the speed of the grid actually changes and you left your speed adjust alone, then the same mechanism is in place where if you have a high Droop here, you're going to get low gate movement. So you can either change the speed or change the speed reference, but the Droop's going to come in and pull it back out. All right, I hope that makes a little sense. That's how it's an automatic feedback mechanism, right, to subtract or add to the speed reference as you're governing. Now here's the actual cutaways. It's pretty neat how this is done in real life. These are the actual cutaways showing this example. You have your equalizer cam. Well, a lot of these were fixed, and a lot of them were also adjustable. So you could have, if it's not adjustable, where you don't have the little thumb wheel, then it's either a 2 or 3% fixed cam. But this one, as you screw it in and out, you actually change the shape of the cam, which changes your Droop setting. And where that cam is it's right here, which is connected to the gate feedback. So as the gates move, the compensating crank rotates and causes the cam to rotate, which then it's kind of a little hard to see. It's a little dark on here. But this actually is a lever that is supporting the speeder rod assembly, or the cup assembly. So this whole assembly in here slides up and down, and this is your speeder spring. So as the gates move, you get this assembly rotating, which then causes this lever to pivot up and down, which then slides the speed adjust up and down. I mean, it's a very simple mechanical feedback, and that accomplishes the Droop function. So you got your adjustment here, and your Droop adjustment here, and your speed adjustment up here. And the speed adjustment, you adjust it by turning the knob. It turns the worm gear drive, which then drives this cup up and down relative to the sleeve. So you can create more tension by cranking the cup up. You're compressing the spring, and then this assembly is going to have to slide back down to relieve that tension. Is that pretty clear to everyone, how that works? Okay. Now, a mechanical cabinet has a slightly different arrangement. And like I said, I'm going to show this from multiple points of view, multiple configurations on the equipment. So hopefully it'll be clear by the end. What we have here is basically the same thing, just packaged a little differently. We have our servo motor down here at the bottom with the feedback. We got our droop cam adjustment, which is slightly different, where we actually have a fulcrum ball that moves in and out. And you can see from the numbers, 0 droop is on the inside, 5% is on the outside. We have our speed adjustment device down here on the side, so that this would be like either your hand wheel on the front, or here it's depicted as more of a thumb drive. And you have your ball head up top, and then of course your pilot valve. Now it's essentially the same thing, it's just a different layout, where if you make a speed adjustment here that raises this end up, you're going to go ahead and cause the pilot valve to move, which then in order to get rid of the speed adjust, you just raise this end of the bar. To put this link back at the null point where it's shown, you have to drop this end back down. Now the amount of movement that you're going to get relative to a gate movement is proportional to where that fulcrum ball is. If it's way on the outside, you're going to get a lot of movement for a given gate movement. But as you move it back towards the center, you actually don't get any movement on the lever because you're centered at the pivot point. It's just another way to do that. That's the way mechanical cabinets operate. And when you go through the setup on that, that's why you go ahead and set the 0 droop, put your dial indicator on there to make sure that your floating lever is not moving when you actually move the gates open and close. So that's really what you're doing. You're checking to make sure that you're not having any input into this pivot point when you're at 0 droop. Right, now here's the more complex version of that. This is kind of the whole ball of wax all put together. Hopefully by day 3, for a lot of you, this diagram will be old hat and it won't be intimidating at all, because there's a lot of stuff going on here, but this is the actual, the full schematic for the mechanical cabinet actuator. But really when you break it down into its sections, if you look at it, everything's just the same as what I showed you. We got the ball head coming in, all right, our pilot valves over here, here's our floating levers, all right, and here's our speed adjustment. All right, it's just a slightly different configuration. As you change your speed adjust, you're just moving the end of a lever up and down, and in order to get everything back to the centered position, your droop has to come in and lower or raise the other end of the lever. It's just very straightforward, and it's connected to the gate position. So once again, you have an adjustment of where the fulcrum ball comes in, and based on how you turn the droop dial, that just changes the pivot point. So even though the diagram itself, it looks a little complicated and overwhelming, when you start looking at the individual pieces, like the gate limits and the dash pot for temporary droop and the ball head assembly, it's all very straightforward. And I think Jerry's kind of impressing that upon you, that the governors are actually pretty simple when you have your basic feedback mechanisms in place. Now, we talked about the mechanical governors, and I just want to say that in digital governors, basically we do the same thing, it's just we do it through calculations. We go ahead and set up an equation where we go ahead and solve and balance the equation and wind up with a resulting error. The basic equation is the speed, which would be your system speed or your turbine speed, has to be equal to the speed reference minus actuator. We say actuator instead of gates because sometimes it's needle, sometimes it's deflector. Times the droop value. So basically, it's a very dynamic equation, and solving for error, we wind up with speed reference minus actuator times droop minus the speed. So feeding our PID, which is a method of controlling the gates with a stability routine, basically you generate your error. You can either change the speed reference, you can change your droop, you can change the actuator position, or you can change the actual speed. So imagine when you're offline, this equation's being continually solved. So you got your speed, which actually is changing because you're trying to synchronize. You got your speed reference, which is changing because you have operator input trying to get the turbine to speed up and slow down from either the operator or the automatic synchronizer, and you have the actuator, which is the gates, actually moving the whole time. All right, so when you're going to synchronize, this equation is very dynamic, and it actually bounces around quite a bit. If we look at the PID that this feeds, you can actually see the error, moving up and down. Now, once you go online, your speed is relatively constant, as I've said, and then your actuator is not going to move unless the operator does something with the speed reference. Right? So that's how the operator can load the unit. Speed is constant, actuator doesn't move on its own, so the operator has to come up and adjust the speed reference, and then he's going to create an error in the system, which will then back itself out as you move your actuator. So you increase your speed reference, you have to increase the actuator position to get this error signal back to 0. Now, if everything's left alone, the speed will change slightly, and you'll wind up with small changes throughout the day on your actuator position without any operator interference, because you've generated an error in this equation. All we're trying to do is just balance these three components out all the time. It's just sitting there balancing it out. And mechanical governors do it mechanically, and digital governors literally have this equation built into it. We solve for it and then send it to the stability routine. So here's a real world example of what's going to happen. We have a generator that's capable of operating one saw. So what's going to happen when the first log is sent through there? What we have here is the load is increasing on that diagram. So basically, we all know from common sense that you go ahead and load up the motor. The actual load of the unit is going to increase. The speed's going to take a dip. And then with temporary droop, we're going to wind up coming back. The gates are going to swing around in response to the load, but then we're going to settle out. Now notice the gates are at a new position because we have to put more power in while we're cutting the wood. So initially we have a speed disturbance. The governor reacts. Now this is temporary droop only. We do not have droop in here. All we have is a dash pot for stability. So we wind up with the gates in a new position to get our speed back to our nominal speed. All right? But now the demand for wood is increasing, and we have to add more saws to our system. So that presents a bit of a problem because we want them all to work together. If we have two units with temporary droop only, what can happen is they can start fighting each other. So we got two saws working off the same grid. This one's depicted larger than the other one. So we go ahead and start feeding wood in, and as we create a system disturbance with zero droop, we can create an instability in the system, because both of those units at zero droop, they want to do everything they can to get that speed back to the original set point. All right? They've been told, go to 100% speed, keep it at 100% speed, no exceptions. So they're going to do everything they can with their actuators, their gates, to go ahead and get that speed back, but they don't know the other guy's there. So they start reacting to each other, reacting to changes, and you can wind up with a scenario where the whole system goes unstable, because the units react as quickly as possible to the load, with some temporary droop for some stability, but it can lead to instability as it was shown. Or, depending on the set points, because no measurement system's perfect, one might see the frequency as a little bit higher than the other one, so he'll be trying to shed his load, and the other one sees it as too low, so he'll be trying to pick up. So you can actually have them going to extremes, where one unit will load all the way up, the other one will shed all his load, but then once he sheds far enough, you can't carry the whole load anymore, so you wind up with this weird interaction where one guy goes all the way open, and then the other one comes back up to some level. But you don't have any control there of the system. You're lucky if it goes to a stable state. I've showed up at sites where the droop cam was mysteriously set to 0, and all the unit would do, it would be fine when you're offline. As soon as they close that breaker, the unit would go just all the way to 100%. Then the operator, of course, would try and get it back down, crank the speed adjust down, and the unit would unload, go in the hole, and trip off. So all it was just a droop cam setting, because without that feedback mechanism, you can't get rid of the error in the speed reference without the actual speed changing. And if you're online, then your speed's not going to change enough to pull that back out. All right? So So you don't want to run units, multiple units together without droop. So what we want is to have, you can have one unit on zero droop, but the other one needs to have some sort of droop on it. So we're going to put permanent speed droop on the system, and as the system becomes larger, each unit that we add will also have speed droop with it. You can have one unit, preferably a larger unit, to manage the zero droop, and have the smaller units have, say, like a 5% speed droop on them. So this is a simple, very simple droop system where all we've done is we've added basically there's no real adjustment on here. I'm not even sure that's, that adjustment would affect other things. So that's not really a droop adjustment, but it's just some sort of feedback, a fixed feedback coming in. So as our actuator moves, we can actually see how we're acting on the pilot valve to cancel out what this side is doing. And of course, we have our dash pot that's been talked about as our temporary compensation for more stability. So now we have a simple droop system. What we're going to see is these response curves. I hope this makes sense. What the different colors are, the steeper the curve, the higher the droop value. So if the unit's going to follow this curve, or these lines, according to their droop set points. So this is a 5%, a 4%, a 2%, and the horizontal line is a 0% curve. Now let me interpret this just for a minute. If you're sitting at exactly 60 hertz and 50% gate, if you're sitting at this point and you're running 5% droop, all right, if the frequency changes on you on the outside world, you're gonna follow this line to wherever that frequency intersects that blue line, and that becomes your new gate position. All right, so it's very easy to predict what these are linear feedback, so you know exactly where you're going to go. If the frequency increases to 61, all right, your gates, because it sees the grid going too fast, it's going to back off the gates until you finally wind up at approximately 20%. All right, so it's a fixed response that you're going to see. So you've basically defined an allowable speed error that's acceptable to the governor so it doesn't freak out and go all the way to its extremes. Right? You've basically created a stable definition for how to behave under certain situations. And as your droop number gets lower, you're going to see a more extreme reaction. As the frequency goes up a little bit, you're going to see much more gate response from the 2% curve versus the 4 and the 5, and you can just see that from the chart. So we would wind up, if we went to 60.5, at 2%, we'd wind up way down here on our gates. Whereas, with the 5%, you've only moved the gates about 8%. And conversely, if the speed drops, you're actually going to see the unit pick up load. So throughout the day, as the grid speed moves up and down, you can watch your governor just pick up a little bit of load and then shed a little bit of load. So the only time you're actually going to be exactly at the gate set point you want is when the speed is exactly 60.0 hertz. All right, if you set it and walk away and the grid frequency changes, you can come back and say, oh, darn it, I'm not at 50% anymore. I'm only at 49. But that's because, and you don't know if something's going on with the governor, if somebody made a change, or most likely it's a change in frequency. So to evaluate what the governor's doing, you have to know what the frequency is to evaluate its performance. So here we are back at the sawmill. Now we got two units running. We got temporary droop only, so that's going to be zero droop. And then we got permanent speed droop on this saw. Right? So we have our speed droop governor here and our temporary droop on the right, both connected to the same grid. So as the load goes up, what we're going to see is, of course, we're cutting wood, so we take on a load, our speed drops down. Now the first unit at 0% droop, his job is to do everything he can to get that speed back up to 100%. All right, so you're going to see a reaction like this, where he takes on the load. This is the gate swinging around. This is the gate position. You're going to see it swing and show a quarter wave decay for a properly tuned governor. But he settles in, at a higher gate set point when the speed finally settles in. So he's satisfied. The zero droop governor is only satisfied when the speed has returned to its initial 100%, right? Whereas unit number 2 that's running 5% droop, he initially picks up the load because we have a speed error. Now remember, the 5% governor, he's following that curve. He's following that blue line. So the blue line told this guy to go to this gate position with this error, but as the error goes away, he's following that line back to right where he was. So you got unit number 1 at 0% has actually picked up the majority of the load, or all the load, and unit 5, load change I should say, and the 5% guy, he's happy as a clam because the speed's going back to 100%. So because of his droop equation, he's satisfied here, whereas the 0% guy is at a new position. Even though the speed's right back where it was, he stabilized at a new position. So you can see the 0% wants to do everything it can to get back to 100% speed, and the 5% droop actually doesn't care so much about speed except for the fact that he's following that blue line. All right? So now if we have both units at 5%, what we're going to see is the same thing where the load goes up, the speed drops off, and we get some recovery as they pick up the load, but both of them are at 5%. You don't wind up back at 100% speed. All right? Because we've told both of these governors, we told them both that it's okay not to be at 100% speed as long as you're following the slope of the line that I've defined for you. It's okay. You're allowed to be satisfied with a speed offset in your final calculations because I've taken into account the actuator position. So without some operator involvement in this system, or the load going back to where it was, where you shed your load, right, back down to 20%, without that happening, you're not going to get back to 100% speed. Now the operator could, if he thinks his load's going to be constant, he could walk up and go to each governor, crank up the speed adjust, and go ahead and get those, and go ahead and crank it up until the gates go open enough to get you back to 100% speed. So without some operator involvement to act as kind of an integrator, you're never going to get back to your 100% value, right? Because they're both running 5% droop. You've told the governors it's okay to not be at 100% speed. So normal grid operations, it's the governor's main goal is to maintain the speed. All right, so all intents and purposes afterwards, the speed doesn't change. So in order to load the unit, we're going to have to make it think it's going too fast or too slow. We've kind of covered this in the background already. So what we do is we bias the speed reference. So when you're online, you move the speed reference up or down, and it'll go ahead and create that error, and it'll move the actuator until the droop function pulls it back out. All right, is that pretty clear how that works? So your speed's not going to change, and your actuator's not going to change on its own. So the only choice you have as an operator to load or unload that unit is to change that speed reference value. All right, and then it'll follow the predefined droop curve and pull the error that you induced. The droop will pull that error back out until everything's satisfied. All right, so once again, on this chart, we can see that we have our speed adjustment. We change it. We go ahead and then if the speed doesn't change, then our pilot valve will move, all right, because of our speed reference change. And then through the hydraulics, we move the gates, and only the droop can get you back. All right. Now, if you're just sitting still and you wind up with a speed change up here, you're going to get the same effect without changing the speed reference. I'm sorry, the speed reference over here. So if you actually get a change of frequency on the grid, you're going to wind up moving the gates, and then the droop is going to come in and offset this pivot point, which will then, instead of recentering this lever, you're going to be recentering this lever, all right? Because you've changed, this ball head is not in the same position. So no matter what changes, whether it's your speed adjustment or your actual speed, the droop's going to come back in and go ahead and nullify that error and make the gate stop moving. All right? So basically, I mean, droop is, it's not a mystery. You know, when you set your 5%, your 4%, you can calculate exactly what your expected gate change is going to be based on an actual change in speed or a change in speed reference. So you know if you're running 5% droop and you do a 1% speed reference change, you're going to move your gates 20%. It's just straightforward linear mathematics, all right? So given that, if we were to see a 1% change in the actual speed or speed reference at 5% droop, we get 1 divided by 5 is 20% servo change. 2%, all right, you just do the math, you get a 1% speed reference or speed change divided by 2, now you're 50%. So there's a huge difference in the operation or unit between a 5% and a 2% unit. You're going to find the 2% unit, you know, it cares much, much more about speed than the 5% unit. All right? And of course, at 0%, you do the math infinity. You're going to do everything it can. It'll do everything within its power to get that speed error gone, all right, by moving the actuator, because there is no feedback. So what will happen is you either go fully open or fully closed if you can't actually change the speed, because say you're online. So here's some normal daily grid variation example. As I said early on, in our neck of the woods, we can go 98 to 02 pretty easily. So we get a tiny little speed change on the grid. At 5% droop, you actually wind up with, just running through the math, you wind up with a little over 0.5% gate. I mean, that's over just a couple of minutes. You can watch the grid go up and down. So you can sit there, and if you're oscillating, say between 98 and 02, you can see a 1.2% swing in your gates. I mean, I shouldn't really call it a swing. I should call it more of a drifting, because it does take time. But you will see motion. And of course, if you're running at 2%, you know, it's even worse. So you can easily see fairly, you know, noticeable changes in your gate position just based on normal grid behavior. I mean, this is a very common number to watch the grid change. So it's okay to have the unit swinging around. The governor's doing its job. I mean, it can't maintain the grid speed, but it can help out. So as your grid starts to slow down, all the governors all over the area try and take on just a little bit of load. And if everybody is running droop and picks up a little bit of load, then the frequency stops dropping. Conversely, if things go too fast, if everybody sheds a little bit of load, then you'll head back towards your 60 hertz set point. All right? So that's just normal operation for a governor. That's why hydro is fairly important for stability, because a lot of people don't run that way. All right? You'll have various nuclear plants that want to go on reactor control, or steam plants want to run off their boiler control. They don't want to be bothered with actually changing with speed and turbine. So there's all kinds of studies that's probably talked about just the importance of hydro and running droop. Now, if your operators take the speed adjust and run it all the way up, you know, and then bring the gate limit down, you know, to lock her in to make sure the gates don't move from the set point, you're actually defeating the purpose of the droop. And it's not only is it bad for the vibrators and the mechanics inside the machine, but it's also bad for grid stability. So if you actually want to check your speed droop, it's pretty easy. We'll say you set your speed adjust to 5%, put the unit online, and put a 1% speed adjustment in. So you should expect, as we had discussed previously, the ratio will give us a 20% servo change. 18 to 22 is pretty good for a mechanical cabinet, although I'm sure they can do better. Is that a good number, Jerry? 18 to 22, pretty good? All right, just want to make sure. So because you're going to get error, you're going to get, you know, because you have mechanical feedback and junctions in there, pins, so forth. You're not going to, you may not exactly see it. But if you're outside of that, you're probably out of calibration. Or you might want to do a little more maintenance on your 90K pins. So the more complex way is actually to put the system on and load it up, record the gate opening and the ball head speed, unload the unit with the gate limit, which basically read that as leave the speed adjustment alone. And then once you open your breaker and you're free to speed up the unit, raise the gate limit out of the way and record the ball head speed, and your droop calculation follows this equation. So what you do is you go online, you go to a fairly high speed reference. The higher, the better. Less linear interpolation error. Go ahead and unload the unit with the gate limit. Open the breaker, and then you can take the gate limit out of the way. I mean, you're not going to go into some wild overspeed because the gates aren't going to get nearly to where they were, because obviously the speed of the unit will change, and that'll rebalance your equation. You're not counting on actuator position to balance you out. You actually will have a significant change in speed, so you shouldn't be too afraid of doing the test. And that'll give you, hopefully, the same number that you see when you're online. So here's just a quick example, 450 RPM, 80% gate. You unload the unit, and then move your gate limit out of the way. You wind up with 466 RPMs at a 10% gate. So you just do your math, run through the math, and then there's your droop calculation. So all this stuff should be in the handout. So if you guys ever need to check that, you can just refer to this page. It's more just shown as a good real-world example. Now here's some data that was actually collected on site. The IEEE testing and the NERC testing. People want to verify that their units are responding properly. So I mean, we do, when we commission governors, like new digital governors, we actually do timing tests where we'll put in a step test and make sure that the governor can do a speedy response. But this is more, if you notice the time frame here, this is more of a long-term trend. Right? So we got about 10 minutes there. So what, this is about 40 minutes or so. And you can see, what you really pick up on is that the grid frequency is going all over the place. You can see it's between these two ranges, right? We get outside a little bit. But this is over the course of a long period of time, you get these variations. Now what they look for and what you want to see is that the gates and the load is actually changing in reaction to that. When your frequency starts dropping, your gates pick up. Conversely, when the frequency goes up, your gates are going to close. So this tells you from this graph that you are actually contributing in a significant way to the stability of the grid by acting in the reverse direction. So frequency variation of 0.06 hertz. Say you think your max gate movement would be 2% calculated, but you wind up with only 1.6%. Question's kind of like, well, why? Why didn't we get where we want it to be? And because you all have the slides, you all know the answers already. Is that what we talked about before? First of all, there's a speed deadband allowed inside the governors. We have a plus or minus 0.01% for a 0.02 deadband that you can pick up on. So you're just not going to, although the newer governors are much more accurate, and actually the old governors, I think they were like 0.004, the mechanical governors. Is that a good number? I mean, it's very, you'd be shocked how well a mechanical governor actually measures the speed of the unit. So first of all, you do have a small deadband that you got to deal with, so you're not going to see every speed change. And then, like I said before, you got mechanical losses in the restoring assemblies, floating levers, got some pilot valve lap going on, some little backlash in the dials, and just no measurement system is perfect. It's really hard to measure a tiny speed change. The equipment has to be capable of measuring tiny speed changes also. So that's it. So that's the end of the presentation. All right, very good. I'll turn it back over to Jerry.
I'm just going to kind of reiterate a little bit about the stability thing. But in the Droop class, we have a magic number, and it's 16.67. And if you divide the Droop you have, like 5 into 16.67, that would tell you how much your gates are going to move per tenth of a cycle. And most of the system people don't work in percent speed. They work in megawatts per tenth of a cycle. So that's a number that'll work. 16.67. If you got 5% droop, that number stays the same. Okay? Okay. One of the other questions that I think you brought up when there is a grid disturbance, there's no one unit that's large enough to be zero droop, okay? So what happens, there's a system computers, they call them load frequency controllers, and they sit there, and as Dan pointed out, the governor can't do anything until there's an actual speed change, okay? Well, the first thing that happens when there's a grid disturbance, the WR squared, or the mechanical inertia of the unit, it absorbs it. And if you've ever been in a powerhouse when there's been a grid disturbance, it sounds like it kind of grunts a little bit, it absorbs it. The next thing that takes place is if you have static excitation, the static excitation can respond before the governor does. So you have a couple things that have to happen before the governor can change, as Dan said. First, the WR squared absorbs it. The static excitation is going to try and keep the voltage steady. And then once the speed does change, now the governor can come in. So the governor's kind of has to wait until there's a disturbance. Once the frequency does make a disturbance, then all the speed adjustments of the governors that are in service start getting pulses to start bring the thing back. Is the guy from Kestrel here? He's not here today? They do WECC testing, they call it. And he'll show you some of that stuff. I don't want to steal his thunder. I got his stuff, but I'll let him do it, okay? So we kind of want to talk a little bit about stability. Now, you notice that when Dan had the drawings and the sawmill there, you notice that the gates moved 1.5 cycles. So we know that governor was calibrated pretty much the way we would do it. The gates were 7/10 critically damped, and the speed was critically damped. Now, on the test questions, when we say if you have droop divided by 0, infinity is the correct answer, right? Or the lazy 8. You know, it looks like an 8 laying on its side. So lazy 8 is also a correct answer. So we went through what water inertias are. And proportional gain, well, I like to think of proportional gain as it's like a teeter-totter. If you got a real heavy kid and a real light kid, you had to change the fulcrum point so that they both could teeter-totter together. So a teeter-totter is like proportional gain. You change the fulcrum point, changes the gain between the levers. Integral gain. How many people in here have a car? How many people in here fill their gas tanks? Okay, if you have a 20-gallon tank and the gas pump runs 4 gallons per minute, how long does it take you to fill the gas tank? You just did an integration. That's all integral gain is. It measures the output of the integration is equal to the time integral of the input. So our gas tank is our output. We're putting so many gallons per minute in, the output just keeps raising until we shut off the gas supply. That's an integration. So it's like filling the tank. And then what is derivative gain? Well, it's how many people in here have stood before the actuator when they've started it? And the gates come up, and now we're got the gates open against the gate limit or the speed no load solenoid. And there's a tachometer on the unit. Has anybody ever watched that? You ever watched a unit start? Well, if you're looking at it and there's an operator with you, the speed will be about 90, 92%, and all of a sudden the gates start closing. You're not at 100% speed yet, but the gates have already started closing. That's because the ball head measures the rate of change of speed, and the fly balls have accelerated out far enough to know that I'm going to go into overspeed unless I get the gates closed. So there's the derivative part of the governor. It's the output from fly balls is proportional to the rate of change and speed of the turbine. So how do we provide compensation? It comes from the dashpot. We had the two components that the governor does. What does it do? The temporary speed droop is called proportional gain. Okay? And the dashpot reset time is integral gain. And the derivative term is KD. Now this is, I'm going to approach this part of the class a little bit different than Dan was talking about system speed versus gate position, right? So what I'm going to do on my graph, I have speed adjustment versus gate position. And this is a 5% speed droop machine, okay? And so once you synchronize the machine, and I can't change the system frequency anymore, if I crank the speed adjustment up, it's going to be like Dan said, if I had 5% speed droop, and I crank the speed adjustment 1%, the gates will move 20%, right? So let's assume that 98% speed adjustment, my gates are at 10%, and I synchronize at this point. If I go from 98% to 99%, that's a gain of a change of 1% speed adjustment, right? The gates went from 10 to 30, the same as what Dan said. So the frequency will do the same thing the speed adjustment does. Now, one of the reasons we do this is to let you know that you have to have endpoints on the speed adjustment. 102.5 minus 97.5 is change of 5%. Everybody agree with that? That's 5% change? Okay. And that's 5% speed droop. It takes 5% change in the speed adjustment if the unit has 5% speed droop for the gates to go 20%. That's why we get that number of 20 to 1 gain. So this is gate position versus speed adjustment. This is the formula for water starting time. It says that the TW is equal to length of the pipe times the rated velocity, acceleration of gravity, and rated head. Now, if we plug, this is typical numbers. If we take these numbers that we have for the penstock, scroll case, draft tube, flow, head, acceleration of gravity, we plug these numbers in, we come up with a number of 1.15 seconds. Now, some people might say, why did you divide this by 2 here for the scroll case? Well, if you all remember what the scroll case looks like, it's big at one end and gets smaller at the other end. Well, it's very hard to integrate that water supply over that entire funny shaped spiral case, so they just average it. Okay. But if you remember now, we've got 1.15 seconds. The TM formula is WR squared NO squared, so we got WR squared NO squared plus horsepower plus a constant in there. And if we plug the numbers in from the sample calculation, I got 5.9 seconds. And what was my water starting time? 1.1 something, right? Well, what's 1.1 and 5.9? 7. I immediately know how far on a mechanical Woodward governor should I have my dash pot open? 1/8 of a turn, right? You were close. That's good. 1/8 of a turn. And that's why I say that if you know the mechanical starting time and the water starting time, you add them together, you're going to get your dash pot reset time. So the governor is gate restoring signal through the speed droop mechanism, provides permanent speed droop. Permanent speed droop, it's permanent proportional gain, and as Dan said, it adds to the stability of the unit. If you take your unit and put 0 droop on it and go to synchronize it, it might be a little bit fuzzy. Crank the speed droop back up to 5%, and sometimes it'll get better. And I just remembered one thing I wanted to say. I have gone out on units, and I've overhauled them and made them, I know they're super sensitive. And then we synchronize the machine, they pick load up, and the operator says, this governor ain't working good now, it's drifting. The gates are moving. Yeah, but if you look at the frequency, you can see that it's following it. They don't realize that those minute changes that Dan was talking about, the governor's going to move. So you have to be careful. You got to make sure if the operator and you're working on the unit says the unit's drifting all over, make sure you know what the frequency's doing. because the governor might be behaving now, where before it just was dumb and sat there and never made any changes. How does Droop provide compensation? When the governor is properly adjusted, the amount of gates are allowed to move for any speed error is determined by the temporary speed droop. I think I told you that. And the reason, anybody remember why we try to recenter the gates after there's been a speed change? We don't want that power reversal to give us too much error signal. So we're anticipating, in other words, when you set your temporary droop correctly, and you'll do this, this is empirical, you have to actually do it, you have to change them. You're looking for the right amount of gate movement so that you got a good stable governor. I mean, if you have too little gain, it takes a long time to recover it. I didn't tell you how long it should be. If you give the governor a 5% error with the gate limit, and when you take the gate limit away, that unit should be back on speed between 6 and 20 seconds. So that's the parameter you're looking for. 6 to 20 seconds for a 5% speed upset. Then your governor is acceptable. So we've talked about the dash pot needle. This here is a curve where it demonstrates, this is the dash pot reset timer TR, and this is the temporary droop. It's a curve such as that Dan drew. It's going that way. And what I'm going to get into is see if I can do this. I forgot what the key word was. But I'm calling in the key word. Put up the Excel spreadsheet. But we want to keep this one going too. Yeah. Just interactive group put up. Make it smaller. Now, while he's doing that, I have to thank Bianca and Jim for this next presentation because I gave during one of the focus classes speed droop, and Bianca said she didn't understand that. So I said, okay, so I conjured up another, what I thought might be beneficial, and I asked her, and she said, I can understand that now. So I let Jim look at it, and he's a whiz with Excel, so I'm not a whiz at Excel, so he made it pretty and did a bunch of other stuff with it that I think is kind of neat, and I want to share that with you. When this comes up, what we're going to be showing you is how the gates react to speed adjustment changes, which Dan alluded to. I'm going to show you how that does that. And then this program will show you how the gates respond. And then as we change the gain adjustments, you'll see that the time for loading changes. What's that?
You're going to have to move it around a little bit,
lost it? Or can't you shrink it a little bit?
If I shrink it too much, it's going to just be impossible to see.
Okay, go a little bit bigger than that. That's probably okay.
And then we'll just have to.
Hang on, okay. Let me take a look at it. That's okay.
It's just the ribbon.
Okay. Okay, let me put this at. So we said that 97.5 to 102.5 is a change of 5%, and that's the endpoints of the curve. 97.5, 102.5 are the endpoints of the curve. Well, let's assume that 10% gate is speed no load. So I've now opened up the unit to the speed adjustment I set from 97.5 to 98. I'm at 10% gate as this graph shows. Now, this graph is running from left to right, and on the y-axis it says speed adjustment. On the graph that Dan had, his y-axis was system frequency. So I've taken the frequency and kind of inverted it because I got a simple mind and I don't understand some of that other stuff. So I had to put it in the form I could understand. So I also know that all governors, regardless if you have 1% droop, 2% droop, 3% droop, 4%, 5% droop, if I set the speed adjustment at 100%, the gates are going to go to 50%. And the reason for that is we're working off of that restoring shaft that moves 60 degrees, 30 degrees either side of center. And if you have a radius, you're going to have nonlinearities if you put all of the movement on one side. So they decided to put the 50% was the ideal spot, then you had equal linearity on either side. So let's take and put the speed adjustment to 100%. So now where should the gates go? To where? 50%, right? Oh, wow, they did that. Now, if I want to go to 70% gate, what should I do? I need to go another 20%, so 101. Okay. There I went. But lo and behold, well, we don't want to look at that yet because I didn't use the other chart yet. So now, what happens if the system frequency got to have an arrow key on here. You're just doing this is backspace, okay. Okay, now, what happens if the frequency goes up 1%? So what would 1% frequency be? If 10% would be 6, right? 66. 1% would be 0.6. So 60.6 should be 1%. Now, where should the gates go if the frequency increases? I put a 1% change in, they're going to change 20%. Are they going to go up or down? Down. So I'm at 70%, so technically the gate should go to, see, I now have a new, here's the 60 cycle curve we started off with. If we have 60 cycles, I'm 97.5 to 102.5. But we no longer at 60 cycle, I'm at 60.6, and now the gate's moved over. So I have gone from 70% to 50%. So I'm going to put this back to 60. I'm going to take the gates and I'm going to put them at 30%, which is what? Now, I want to load the machine up to 100% gate. Where do I go to? What speed adjustment will make the gates go to 100%? A 100, right? Okay, let's see how the governor, we know we went 20%. How did the governor pick up the load? Okay, there's our response curve, all right. Well, let's see where we're at here. It says my dash pot is open. I close the dash pot, which means I have no dash pot bypass. Look how damn long it's going to take me to get loaded. So I also have the dash pot reset time is 10 seconds. We can put 7 seconds in there. You notice it helped? Well, how about if I put the temporary droop down to like 80%? That even helped. I didn't want to be in desktop. And now if I'm going to put it on the dash pot, I'll close the breakers if we went on the line. Now it's a lot better. So that's what your gains do for you. When we change the dash pot, temporary droop, the dash pot reset time, and we close that dash pot breaker. So that's kind of droop in a different way. And I have to check the program to find out where the heck we're at here. We're supposed to go until we're past it. Yeah, we sound the brake bell. Sorry about that, guys. There's always supposed to be somebody that tells me I'm kind of long-winded that it's time for a break.